All right, it's good, yo. Went for another daily. Just finished the day 11th a couple minutes ago and posted the video. That one was a hard one, so my brain's kind of fried right now, but let's see how this one goes. Uh, bu- 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 So day 13. Minim Minimize the maximum difference of pairs. Oh my God, I'm done with pairs, dude. Holy daily 2616. I'm done with pairs, dude. Oh, maximizing, minimizing, all this kind of stuff. Okay, let's see. Given a zero index integer array, nums, and an integer p. Find, okay, integer array, okay, integer p. Okay, find p pairs of indices of nums such that the maximum difference amongst all the pairs, wait, the max, that the maximum difference among all the pairs is minimized. Also ensure no indices, no index appears more than once amongst the p pairs. Note that for a pair eliminating xij, the difference of pairs okay, is the absolute sum, where eliminating the absolute value of x. Okay, return the minimum maximum difference among all p pairs. We define the maximum of an empty set to be okay. Okay, so we need to find p pairs of indices of nums such that the maximum difference among all the pairs. Okay, the max difference pairs. Okay, this is what is going on here. Find p-pairs of indices of nums such that the maximum difference amongst all the pairs. So we have a couple pairs. We need to find those pairs such that the maximum difference among all the pairs is minimized. Okay, let's see an example. See. The first pair is formed from indices 1, 4, 0, 1, 2, 3, 4, 1, and 1, and the second pair is 2 and 5. So the maximum difference is the max of 1, 4, duh, duh, A 0, 1, which is 1 and 4. Oh, okay. So 1. So this is pretty much in this case, it's going to be the pair that returns the minimum difference. So I would say 1, 2. Oh, 2, 2, 0. Okay. Oh, it's absolute. Okay, so absolute. Okay, so that's 2, 2. If it was not absolute, then it would be 1, 2, but it's absolute. So that's this 1 and 3 from a pair. The difference of the pair is 2 minus 2, which is 0, which is the minimum we can take. Okay. All right. Okay. Let me. Gotta whiteboard this thing. Okay. Okay. So let's see. Okay. So in this case, the maximum difference is the max. We need to find p pairs. I don't see why this p is useful in this case, right? Oh, because it's max. Is the We have to minimize the max of this difference. Okay, so okay, okay, so the min wait, do we have to minimize? Okay, so we have to make pairs of numbers such that we want this thing, this difference to be minimized, as well as this one also must be minimized. And then when we take the maximum, we're gonna grab the minimum of those two. Okay, So my first idea here is that okay, so let's say how can we minimize this thing? Oh, also let me see the constraints. Can we always okay, we can always make pairs. Okay, so my idea here is like let's say we have a number A and a number B. We take the difference, right? If we want to minimize this thing, we kind of want to like make these two elements as close as possible, right? Let's say we have one, two, three. Oops, let's not one. Let's say we have. Can we choose any pair? Well, let me see the okay, AJ. Since it's absolute value, doesn't matter if we do like I minus J or J minus I, right? Doesn't matter. Okay, so let's say we have one, three, one, one, two, three, four. How are we gonna I'm gonna minimize the maximum difference of pairs. So we want to grab elements that are closer together, right? So if we have a 1 here, the closest element we have here from 1 is 2. And then the closest element we have from 3 is 4. So it's going to be 1, 2, 3, 4. That's 1, that's 1. Max of 1, that's equal to 1. So it's kind of like we're sorting this thing. So 1, 2, 3, 4, and we grab it adjacent numbers, right? And we want to grab those adjacent number p times. And then in the worst case, p is going to be equal to n divided by 2, right? P is equal to n divided by 2, and then that's going to be n squared times. So I'm not sure if, let's see. I could just like, I want to try this. 'Cause I think, because I could just sort and then grab 2 by 2. Uh, oh, you know what? Okay, so then we need to return the index, right? Oh no. Wait, what would we have to return again? Oh, okay. No, I have to subtract the index. Oh, you know what the problem is now? Okay, let's say, oh, I saw another problem here. Well, let's say we have one, so let 1, 3, 2, 4. Mm. It's the absolute value. I feel like we can just do, we can't have, can we have negative numbers? We can't, right? Nope, we cannot. Okay, I think that should work. We just, let's see if we, well, I wonder if I should want to do the sorting thing. Because we could just sort and grab p pairs, but that's going to be n log n. I wonder if we can do it all of n time. No, that's going to be n log n, right? It's not, it's not going to be n squared. Because we can sort, grab 2, 2, 2. Let's take a look. Let me try the sorting first, and then we can think about something else. This pass nums the sort, and then best is equal to -1 because we're never gonna have something than that. But we can have like 2, right? And then the difference would be 0, so we can have 0. Well, the only thing that actually keeps 0 because that's the best. Anyway, okay. So as we go for I in range P, no, not P, from 0 to, let me do equal to length of nums, and taking step of P. So let's say we have and oh, 1, 2, 1, 1, 1, 1, 2, 3, 7, 10. We're gonna go 0 and then 0, 0 plus 1. And we're gonna go should take step of 2. We now want to go to P. We're gonna go. We're gonna go P. Not sure about that one. Let's see. So we're gonna set 0, 0, 1, and then we go down here. Uh, yeah, that's right. So 1. We're gonna have 1. Let's say P is equal to 2. P is equal. P is equal to 2. Let me put this close. Here we go. And we're gonna grab 0, 1. So start with 0, we go step by 2, right? So 0, we're gonna grab 1. And 0 plus 1 equal to 0, 1, 2. We're gonna grab 2, and 2 plus 1. Okay, and when we're gonna go here? So it's gonna be n is equal to 1, 2, 3, 4, 5, 6, divided by 2, 3. So we're gonna go up to 3. So 1, bam, 2, 0, so 0, we go up to 3. So 0 plus 2 is gonna be 2, 0, 1, 2, bam, 2 plus 2, 3, 4, boom, we done. Okay. Best is equal to the maximum of best, and uh, the absolute value of nums index I minus nums index I plus 1. Return best. And I doubt it's gonna work because probably gonna get some time limit, but yeah, let's see. Oops. Uh, okay, so p is equal to 1. So we have 1, 2, 2, 4. Oh, the answer should be, let's see. So if order gonna be 1, 2, 2, 4, we only need one pair. So oh, you got 2, 4. That's why I return. I probably return 1, right? I return 2 with 0, yeah, because 2, 2. Interesting. Okay, so this is not gonna work. Yes. I mean, the only case that when we have not really. Okay, this is not gonna work. You need to find a different way now. Uh, okay, so let's say go back to the white board. Okay, so that's not gonna work. Let's try a different approach here. Mm, let me think. We might, let's say mm, oof. Let's think. Let's think. Um, we definitely don't have to worry about the order because we can have like 10, 3, 1, 1, 7, 7, whatever, right? I'm not worried about that part. Let's see. Mm, in that case, for example, that we just saw here, 4, 4, 2, 1, 2. When p is equal to 1, how do we know that we want 2 and 2? We need the closest number to 2. Oh, wait a second. Okay, so what if we go through the array and then we say like, okay, so what does it mean that a number is closest to itself? Oops, sorry. No, that's not what I want to say. So let's say we have A and B, A, B, and C. What does it mean for A to be closer than B, then B is closer to A, then C is closer to B? So how we calculate is pretty much the absolute value of B minus A. If this is greater, then if it's smaller than the absolute value of B minus C. So if the absolute value of B minus A is less than B minus C, that means that A is closer to B than C. So what we can actually do here is kind of like go over the array maybe, and then we track how close the difference between myself and the elements, right? Okay, so let's see. Basically, we have 4, that's just 4. In this case, we have 2 and 4. The difference between 2 and 4, that's 2. Now 1. No, not sure this is gonna work. Hmm. Because the idea here is that we want difference between this 2, this is between 1, and then 3, and this is 1, 0, 4. Ooh, it's hard here. We don't want to do it squared, right? Pretty sure we can do this in all of n time. Uh, there's some data structure that we can use to maybe something similar with the odd even frequency, maybe like some cadence algorithm. I'm not sure. Let's see. -1, 2 -2, 2 -4. Huh. 104, 132. Because the problem is that we want e elements, right? Let's try a different approach here. Like, let's say we have. Oh, I want to keep this. So let's say we have 4. We can either choose 2, 1, or 2. If we choose 2, no, that's not. No, no. Nope, never mind. Hmm. I don't know what's the. Maybe sorting is not that bad. So we can sort. But the problem with sorting, like in this case, we have 1, 2, 2. Oops. 1, 2, 2, 4. But then, oh, maybe because we don't want to go with 1, 2. We actually want to go p is equal to 1. We actually want to go 2, 2. Maybe, wait, what is this? Maybe, oh, that's another thing too. Like, if p is equal to 1, then the answer is 2, 2. But if p is equal to 2, then the answer is actually 1, 2, and 2, 4. This will give you 1, this will give me 2, so this is 2. Because if we choose 2, 2, and 1, 4, that will give us 3 as the answer. Okay. Um, okay, I'm kind of confused now. I'm not sure how I'm gonna approach this problem. Let's see if there's any hints. Okay, let's see. Maybe the answer the array should be sorted for. Okay, I got that part. There's search. Okay, let's see if there's a. I would never thought about binary search in this case. Binary search on what? What if we have this 3, 4? Wait. No. We go 3, 4. This is equal to 1. Now, how would binary search will work here? So we have 3, 4, and we can go to the left, to the right, right? How would you know when to go to the right and when you go to the left? So I don't think this will work. Maybe what we can do here, gosh, let me think. Binary search. How can we use binary search to solve this, dude? So it's actually binary search, right? Hint. Can we use binary search here? We grab this two. How much we know when we go to the right and when we go to the left? Hmm. Those I don't see how binary search works here, honestly. Because we can actually, like, okay, so we get to the middle, we can have three candidates. This, this. So if myself is, so 3, 4 is the smallest one. What if 3, 4 is the smallest one, right? Let's say, what if we had like, so we had two cases, right? Let's say this 3 was actually a 4, right? Um, if this 3 was a 4, then we grab this thing, is equals to 1, right? So this is the case. And we will return this. So 0 is the minimum value that we can have. Now, in here we have 1. Well, what if we wanted 2? If we want 2, so this we must have this, and must have this. What if this is like 3, and we have p is equal to 2? Then we don't actually want this, right? We actually want 3 and 4, and 4 and 4. 0 and then, oh my gosh, you have so many cases that we have to consider, dude. How can we use binary search here? I have no idea. Mm. How can we use binary search? So, okay, so what does it mean when we sort the array? 1, 2, 3, 4, 4, 8. What does that mean? So we have elements close together, right? So we can I think we can actually do this. The only thing that's tricky here is the P. But like we can go to the middle, bam, grab the two elements. And then the problem is how oh, there's no indicator that will tell us to go either to the left or the right, right? like how do I know to move to the right depending on the calculation of the middle? So let's say like in this case, instead of one, let's say we had two. So if we had one, that's the answer, right? But since it's two, since it's two, we're actually gonna grab this, and then the response will be one. I don't see how binary search will help me here. Okay, so okay, let's say this P here. If P is equal to one, no, we need to take P as like we have like a base case, just one, right? And then we grab the middle. If P is equal to one, do we return this? Oh wait. Mm, let's get this out of here. Okay. So let's say P is equal to one. If P is equal to one, we compare this. But if P is equal to two, if P is equal to two, do we want to grab this? No, we want to do this, right? Okay, so how can I know based on P? So okay, so if let me grab all this. There you go. Okay, so P is equal to two. Okay, so if P is equal to one, we actually want to return this. But if P is equal to two, we actually want to return this and this, right? So if P is equal to one, we're going to return 4. If P is equal to two, we want to go to the left and to the right. Yeah. Okay. So wait a second. P is equal to one. Then while P is greater than zero, we check this and we check this. Which one's better? This is better. So bam, go here. P goes to zero. So if P is equal to zero, return. P is equal to two. Go here. P is equal to two. Uh, who's better? Here or here? P is equal to two. We need to check if P is equal to one, then we turn the best between this, and this. If P is equal to is greater than one, then we're gonna go minus one. Oh, you know what? If P is greater than one, we want to actually want to grab the greatest in this case, right? So the greatest between myself here and here. Actually, maybe just here and here, right? If it did, okay, so if this is bigger, then which one? We want the largest one. So bam, P goes to one. So one, we're gonna go here or here. That work? So the idea here is that let's say we have 2, 3, 4, 5, but then we have like 1, 1, 6, 6 here. And then P is equal to 2. Oh my God, my writing is horrible. Okay, this is the example that I'm kind of like scared about. So 1, 1, 2, 3, 4, 5, 6, 6. P is equal to 2. The answer in this case is equal to 0, right? Because 1, 1, 6, 6. Okay, let me get right here. Okay, okay. Okay, so we go to the middle. Go to the middle. The 2, 2. This is the middle? Yeah, okay. 3, 4. So P is greater than 1. So we're gonna return the maximum between here and here. So here it doesn't matter, right? Doesn't matter. So we go here, for example. P is equal to 1. Nope, that doesn't work. Oh my gosh, dude. Dude, what is going on? 1, 1, 2. Yeah, that's valid. That's valid. That's sorry. But like when we get to here, how do we know about the existence of 6? Wait a second. Oh no, you know what? No, 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 no. Let me do th- this maybe. Oh, but then we're gonna go here for sure. Okay, so I'm trying to find like counter examples here for why this because okay, so if you go to 3, 4 and we check here and then we check here, the thing that we would actually go here, right, and then go here, and then go here. Wait, one goes to one, then goes to 0. Okay, so what this is? Oh, you know what? We actually do need to do. Oh my God. We do need check for 3. But the idea is like, if I got, if 3, 4 is the smallest between all these, then we subtract 2. Okay, so in this case, do we want to do strictly smaller? Because because 3, 4 is 3, 4 smaller than 2, 3. Actually, no, but it's equal. It's equal. So, ooh, okay, so it's equal. If it's equal, that works. Yeah. So 2 goes to 1, and then we actually move to here because we counted this as a pair. Now, what if this one is greater than this? Then it's not. We go, so the smallest one in this case is here. So in this case, we don't want to check with the right side. We don't want to check with the right side, right? 34, because we don't want to do this, and then when we get to here, we don't want to do this, right? Because this is already a formed pair. Oh my gosh, dude. 34. We want to check if this is a good pair, or this is a good pair, or this is a good pair. This is a good pair. So we go to here. We don't want to check here, right? We actually want to check myself and here. This is better. So we don't increment. Actually, E will go to 1 in this case. This is better. So boom, goes here. And then it's binary search, right? So we go here. Oh, oh my gosh. We have to check if this is better. This is the best. Oh, this is the best. If this is the best, we go from 2 to 1 and we do binary search. So it's actually going to move to here, but I is equal to 1. Boom, return. Well, let's say this is 7. That's going to be the problem now because let's say this is 7 and we decided to go here. What is the answer in this case? The answer is here. So 3, 4. Can you go here and then go here? So if we go to the left, boom, go to here, and we check with this. Left doesn't have anything, and here. Do we want the gray? Yeah, the greatest one. So this one will be either here, doesn't have anything here, and doesn't have here. So this is the best one. So bam, 1, 2, just one. Now, what if we go to the right side? That's just 8. Oh my God, you don't want to do that. Uh, let's see. This is 8. We will go here and go here. Oof. So we're gonna here. This is good. And then we're gonna move actually to here. Then this. Not only is that, what if the answers are all on the left side? And then here on this side, we only have like huge numbers. So for instance, let's say we have like 11, 20, 40, right? And then p is equal to 2, then the answer should be 1. But if you go to the 2, 2, 2, it's okay. And then we will move to the left side. Yeah, but then we wouldn't go, oh, but we want the smallest. What if p is equal to, that's the even worse case. Oh my gosh, dude. Like, what if p is equal to 4? 1, 2, 3. I can do that. So the answer will be, it is valid. Okay. So So the answer would be 1 with 1, and then 2 with 3, 4 with 5. Huh. What if we do 4, 5, 3 with 11, 2 with 20, 1. Oh, this is not valid. Now I just realized it's not valid. This is valid, right? Let's say we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I need to make sure this is 60, this is 40, this is 20, this is 11, oops, this is 5, 4, 3, this is 1, 1. What if we start in the middle, 5, 11, and then we go, this is one pair, P minus 1, and then bam, that's not gonna work, you know why? Because with P is equal to 2, then we actually don't want that, right? Does it matter? It does matter, yeah. Sure, P is equal to 2. This is 1, P is equal minus 1. Goes to 1. 20. Oh, that's not gonna work. Because the answer in this case would be like 1, 1, and then 2, 3. Okay, I'm gonna look at the solution tips here. Yeah, it's like hard. Not a tip. Sort. Oh, not a tip. What a tip. Hint. To no follow hints. Okay, I'll probably let's see if there's any better way of doing it. I don't. I try. There's no way my search will work in this case. I kind of like the idea of sorting the array, but I'm confused on. Okay, 1, 1, 2, 3, 4, 5, 11. Okay, another idea that I had was like, let's keep this simple. Let's see p is equal to 2, then we want 1, 1, 2, 3, right? So this will work. But let's say we had this. Let's say I have this. So I will grab 2, and then we'll grab 3. You know what? Let me go here, and then here. If p is equal to 2, we grab this. If p is equal to 1, we grab the maximum. If p is equal to 2, we grab this, move forward. P is equal to 1. If p is equal to 1, we grab the maximum between this and this. If p is equal to 1, we grab the max this and this. Now, let's say we had is equal to 2. We grab this and this. P equals to 2. Grab this, move forward. P is equal to 1 now. The max between this and this. So that should work. Now, let me think. If P is equal to 2, if because for the idea for this case, like we would have 1, 2, 2, 1, and P is equal to 1, right? So we go here, P is equal to 1, then we don't want to go this, we're going to either go this or here, right? Oh, I saw another problem here now. So let's say we have one, two, three, four, five. P is equal to 2. We will have bam, bam, bam. Oops. Oh my God, how do I do this? I'm gonna have this. Good. Um, then I have this. P is equal to 2. Go all the way here. Now P is equal to 1. We grab the mass in between those two and those two. But that's not right, right? What if? No, it's not gonna work. Okay, it's hard. Uh, maybe a DP approach. We can either grab this thing or we can grab this thing. That's not gonna work because if we grab this, wait, can grab. So think about grabbing this thing or grabbing this thing. But if P is equal to 2, let's make this. Yep. Okay, if P is equal to 2, then we can grab this and this. This give us 2 and make this 5, obviously. Okay, so we can grab. So if P is equal to P is equal to 1, we grab this. P is equal to 2, we grab this. Okay, let's get rid of this. If P is equal to 2, we grab this. If P is equal to 1, we go with this. If P is equal to 2, we grab this and this. Because if we grab this, and then that would be 4. We actually want to do 1 and then 3. Mm. Okay, so I'm wondering if is there any way we can, instead of using the actual number, we actually use the differences. So like maybe we say, oh, we can grab this pair, or we can grab this pair. And then if we grab this pair, then we can grab this pair. Or if we grab this pair, then how are we gonna go from here? Okay, let's see. One head and heads or something. Okay, DP won't work with purple. I don't see how can we get binary search work in this case? Okay, so what is this? 1, 4. 1, 4. 1, 2, 2, 5. How can we get binary search to work here? P is equal to 1. P is equal to 1. We'll grab this. If P is equal to, oh, we actually want to grab this and this, right? Oh, wait, no. Because the problem here is like, we're gonna have like a bunch of numbers over there, a bunch of numbers over there. In binary search, uh, let's see. How do we know when to go to the right and when to go to the left? Let's say like those two pairs give me the same difference. Like, how do I know to go to the right or how do I know to go to the left? Exactly. Okay, same index can't be repeated in our pair. Okay. Binary search of differences, but I still don't know how to go for that one. Like a binary search of differences. One, two, two, four. One. Oh, wait a second. Two. If P is equal to 1, we have this, the, no, anyway. Oh my gosh, dude. If P is equal to 1, what if we do 1, 0, 2, middle. P is equal to 1, return 0. Else, can go to the smallest one, and then p minus 1 is equal to 2, go to smallest one, p is equal to 1. P is equal to 1, boom, return. Oh, to this, the largest one, actually, the greatest one, yeah. What's this? Let's try the binary search of differences. So this is 1, this is 0, this is 2, this is 1, this is 0. So p is equal to 2. The answer should be 0. So go to the middle. 2. Uh, p is equal to 2. It's greater than p is greater than 1. So we're going to go to the greatest of those two. It's here, p minus 1. P minus 1. In case we were. The other one was 102, right? Yeah, so in this case, we just return. In this case, we moved to the. Oh, we actually moved to the middle. But if we choose 2, this is 2, we can't choose this one because we're using the same index. No, it's not wrong. So let's say we have like A, B, C, D. We can have A minus B. We can have C minus D, or we can have B minus C. So if we choose B minus C, we can't go to here and we can't go to here. Oh my gosh, dude. Goes B minus C. We can't go to the right, can't go to the left. Yeah, I think my binary search approach is kind of like sketchy in this case because we're thinking about we sort 1 minus 2, that's equal to 1, 2 minus 4, that's equal to 2, 5 minus 5, that's equal to 0. If p is equal to 2, we want 0, right? So we go to the middle. Let's actually do those elements here. Okay. So let's put 1, 1, like 7 maybe. And then let's do p is equal to 3. So in this case, we have, what's the answer? 1, 1, 2, 2, then 4, 5, right? Oh, no. 1, 1, 2, 2, 5, 5. Answer is 0. Let's see if we can get 0. So this is 0, this is 1, this is 2, this is 0, this is 1. Go to the middle. Uh, is equal to 3. We go to the middle of those two, then p is equal to 2. We're actually going to do 0, 1, 2. But 0, 2, 0, 1 is going to go here. We're going to go from here to here. Nope. Actually, want to go left and right, right? So, oops. Okay, go here, here. Then we have the middle. We want the biggest between those two. This is this. So this is the middle. And then B goes to 2, which 1 goes to greater. So this is 2. We're done. So we're trying to in this case, but we don't want to. Hey, I'm done, dude. Whenever you kind of like minimize or minimize, so it's often the optimal solution. There's no helpful answer. Let me go solution. Ah, I'm done. Oh, imagine trying to form p-pairs from a list of numbers such that the largest absolute difference among all these pairs is as small as possible. But there's a rule. No number can be reused in more than one pair. So how can we make these pairs smartly? We sort the numbers so that the closest values are next to each other. Then we use binary search to guess the minimum possible value for the maximum difference. For example, for every guess value x, we really try to form p-pairs, where the difference between each pairs is less than or equal to x. We can do that. Maybe we can, if we can do that, maybe we can try even smaller x. If not, we have to increase x. Comment. Oh, oh my gosh! I think I see now. The binary search is not. Oh, I forgot this was a thing. Because the binary search is not on the number itself. It's on the difference, the difference you can reach from forming those pairs, right? Set binary low, okay. The maximum difference in the array, and then we keep trying to find. Yes. Minimum, okay, minimum is equal to 0, high is equal to largest difference in the array. So nums index n minus 1 minus, okay, while low is less than high, due at the minimum, the mid, this is how low and high over 2, try to form p-value pairs such that each pair's difference is less than or equal to mid. Okay, if possible, try a smaller mid, so high is equal to mid, else we're gonna go, okay, greedy pair formation. Loop over story array. If there are adjacent pair where the difference is less than or equal to minimum, we count it and skip to, oh, so we have to keep updating p. else we move if the oh I see. Huh. So the idea here is that maximum difference in this case is 7 minus 1, which is like 6. And then the middle will be 3. We're going to try to form. Let's just skip in this part. Through the Fourier array, if there are additions pairs, different count it and skip 2 indices. Else we move one step. Okay, one pair, two pairs, three pairs. This is good. So now we're gonna go to five. Oh my gosh, dude. From zero, it was 0 and 6, and now we go from 0 to 3. Now it's 1. This is valid. This is valid. And this is valid. Oh, this is not valid. If this is not valid, we skip this. Now we try this. This is valid. That will be log and login, maybe. Maybe like login, yeah. Because the maximum difference can be the number of elements in the array, right? Okay, I see now. Okay, I see now. So idea here is pretty much we set the left pointer to be 0. No, actually, yeah, that's 0, and then the right one is the larger difference, which is this element minus this element of the opposite. So 6, and then we go to 3, try to find out p pairs with 3. If we can do this, then we go to the middle and try to do even a smaller one. If we can, even a smaller one. And then if we cannot anymore, we try this. Uh, let's say, okay, so this case we were able to. So 1. Now we try the mid. It's actually 0. So this is good. This is not good. This is good. This is not. Oh, this is good. This is not good. This is good. We were able to. So now it's gonna be 0 divided by 2, which is also go to 0. Okay. So yeah, I think I got it now. Dude, oh my gosh, dude. This was I always forgot that we can. So I always think that binary search we always have to do in the array, but I remember there was another question similar to this where we had to like use binary search not on the elements, but like on some specific value. So left is equal to uh nums dot sort max diff is equal to nums index 0 or minus nums index 0 left right is equal to 0 max diff a left plus the r at the end of return left um r mid is equal to oops Four, five, three, four, five, eight, four. Left, left plus right. Number two. The mid counts equal to 0, while for I is equal to 0, while I is less than or equal to n. Okay, so we're gonna loop over the array now. So I'm not walking through what I'm doing here. So set the left and right to be 0 and then the max difference. And then while left is less than right, we're gonna calculate the middle difference that we are targeting. So let's say we have 0 and 6. 6 is the max difference, 0 is the minimum. We go to the middle, which is 3. So we're trying to form key pairs that have difference equal to 3. And if we can make it, then we can go even smaller and go for that one. All right. Okay. Comes to 0. Let me. Okay. Okay, because we don't want to get the last element. So if nonce index I minus nonce index I plus 1. Take the absolute value of this thing. Absolute value of this thing is less than or equal to mid. Then we formed a valid pair. I was here, I plus 1, so I plus 1, I plus 2, I plus equals 2. Count plus equals else, plus equals 1. If count greater or equal to p, that means that we found more than p good pairs, so we can go even more greedier. So right is equal to mid. Uh, else, if we weren't able to find this, that means that we went too small on the difference, so left is equal to mid now. Maybe this is it. Not sure. Let's see. Gonna get some error for sure. Okay, yeah. I'll blah, 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 blah. Oh, sorry. It's more right here. I think so. Am I? Oops. Am I? Oh, yeah. I don't think I'm okay, that's equal to right. Means it's equal to uh, all I is less than this. Let's see. Test on myself. I think I got like a infinite loop somewhere. Where's this one? 6. Yep. Okay. I'm missing some. Left go to right. I see the 0 to 6. The middle is 3. So now we want 6 to go to 3. 1, 0 to 3. That is equal to 1 goes to 1. Let's say 1 is still good. So 3 goes to 1, 0, 1. 0, 1. So this is 0. So either or it will change to 0. What's wrong here? This? Wait, what? Oh, 0, 1, 0. The same thing. It's not like this. Oh, this is right. If count, wait, but this, this sort of. If if we were able to make key pairs with the mid, then we should shift. Oh, but we don't want mid, right? We don't mid. Right is equal to -1 plus 1. We don't want it. This game is 0, which is not the answer. Let me try right. We have the same one. Yeah, we have. Okay, so now this one game is 0. It's not the answer. Um, uh, uh, counts where they go to be 1. That almost sounds about right. The max diff is equal to the last element minus the first one. Which is where we're going to start from 0. Count is equal to 0. While I is less than, because we don't want to go to the last one, right? If absolute value of known minus is less than or equal to the mid, we made a pair and we increase the count. Now it's gonna skip this pair at 1. If count is greater than or equal to p, then the right one goes to the middle -1. Else I do the 10, 1, 2, 7, 1, 3 is equal to 2. Alpha should be 1. Let's see. Oh, what's going on with LeetCode recently? It's kind of like impossible question, dude. Oops, too large. Okay. Okay. In this case, we would have 1, 1, 2, 2, 3, 7, 10. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This. So 0, 10, go 9. I'm gonna try to find 9, so 1. All is gonna work. So 0 through 9 divided by 2. 0 plus 9 divided by 2, that's going to be 4.54. So good, good, good. So now we're going to try 2. Also 0, 4. We're going to try 2, 2. So good, good. It's not good, but we have 2. Okay, 2 is good. Now we try 0 to this is 1. Nope. Good. This is good. 1 with 2. 1 with 2 is good. We're trying 1 now, so this is good. This is not good. So 1 was not good. So we went from okay, so now we got 0, 2. Now we want to go for 1. So 1, 1 was not good. No, that was the problem. Okay, so if oof. So now let's try 1. So this is good. I'm trying 1. Let's go back to 2 just in case. So this is good. This is good. P is equal to 2. P is equal to 2, right, in this case? Yes. Okay. P is equal to 2. So this is good. This is good. Now, now let's try 0. What 0 to 2? Meter is equal to 1 now. So this is good. This is good. So 1 is good. So now we go 0 to 1, which is 0. This is good. And though we don't have anything good now, so we have only 1. Since this is not good, we okay, now we stop. We have 0 and then we have 1. Uh, I'm both in 0. I should want to go. Let's see. 0 through 9, 0 to 3. Yeah, 0 through 9. Okay, let's see if that makes sense. So 0 through 9, this is good, and then we go 0 through 3. Mid is 0. It's 1. 1 is still good. Oh, actually, uh, then we go the minimum is 1. We try to find, so this is good. This is good. So now we go to 0 through 1. I'm wondering why that one. Oh, actually, if it worked, I would go for, oh, the middle is 1. So I would go from 0, 0. And then these ones didn't get updated. Okay. So while left equal, maybe? Oh, now it got 0, 0. Um, which does make sense, yeah. In this case, right here, so this one worked. 1 is good. Oh, we want to actually. Oh wait, no, no, no. Okay, so when it doesn't work, then we want to skip. When it works, we want to keep the middle. Oh my gosh, that was a problem. Pretty sure that was a problem. Because when we find a valid pair, we still want to have that middle as a candidate, right? But when but if it's too large, then we already know the middle is not a good option, so we can skip that. There you go. Oh my gosh, dude. But yeah, here was like pretty much uh the binary search is on the range for min and max difference possible among pairs, not the elements of nums themselves. All of that was the thing, like why you need to binary search on the differences. That thought was like you create a from the original array, you create a difference array, and then you do binary search on that. But it's actually that's what it meant by difference is that you actually go between 0 and the maximum difference that you can get. Okay, dude, these daily questions are too hard, man. Okay, I think that's it. Thank you all for watching. See you guys next time.